In this talk, we present our super-resolution method based on real raw data. Today, digital zoom is necessary for devices with limited optical zoom capability such as smartphones or consumer-level cameras. Most of SSR methods work in the RGB to RGB domain. Although a large amount of training data is available, the complex ISP pipeline of the camera is ignored. Here is a typical camera imaging pipeline. The whole complex pipeline will make the linear raw image into the nonlinear RGB image, and even lose some details. Some works take a step further by designing models in the raw to RGB domain. However, the model learns not only the super resolution but also the pipeline of an ISP, which greatly increases the complexity of learning. So we think about whether raw to raw is a better choice? This question we put on the back to answer. On the other hand, according to the degradation function, SSR is a highly ill-posed inverse problem. Many learning-based methods process all real-world images in one network. This ignores the degraded kernels. There are some classical blind SR algorithms that use a two-branch network to estimate the degradation kernel, thus achieving better performance. But this method needs ground truth kernel for supervision learning, while the kernels in the real images are unknown. Inspired by the recent progress, we introduce a subspace constraint. This subspace constraint reformulates the ill-posed SSR problem into a better-posed one. Next, we explain why to exclude the ISP and work in the raw-to-raw domain. We explore the estimation of degradation kernel at each ISP step. Based on this degradation kernel estimation equation, we notice that the estimated degradation kernel distributions before demospace step are closer to ideal Gaussian distributions. In contrast, subsequent treatments significantly altered this distribution. We also fit each kernel to a Gaussian distribution and average the fitting error. The mean fitting error has also increased by 8 times after demospace. Thus raw images will reduce the difficulty of kernel estimation, which motivates our method to work in the raw-to-raw domain. Next is our framework. Firstly, we capture a raw image Y as the input and send it to the two-branch network in parallel. Now we have the image basis of X and kernel basis maps of K. Given the input Y and basis of TOS subspaces, the X and the K are jointly estimated by minimizing the degradation function. Finally, X is sent to an existing ISP for further processing into RGB format. The above is the framework of our algorithm, while the specific steps for minimization of the equation can be found in our paper. Next is the experimental part. The real raw data we use are from two real datasets, real SR and SR raw. We do pre-processing to align raw image pairs. This table compares two classes of methods. The class 1, assuming the degradation model is bicubic downsampling, the class 2 requires external kernel inputs. It can be seen that our results are significantly higher than these methods, which also indicates that their assumptions for the degenerate model are too simple. Here, we compare with 4 real models. The first 2 are working in the RGB to RGB domain and the second 2 are in the raw to RGB domain. We can see that our method is also significantly better than these methods. Next is some comparisons of the visual quality. This figure shows that our font is more complete and clear. This image clearly shows that we have recovered the texture details more accurately. We also conduct a zero-shot transfer comparison. The camera types of the two datasets are different, and the symbols indicate that the method was zero-shot transferred to real SR, otherwise it is the method that was trained on real SR. This figure shows that our generalization results are not only significantly better than the two raw to RGB methods on the far right, but even better than the RGB to RGB results. We also do ablation study to analyze the effectiveness of the algorithm details. One is the different model variation. The first one indicates that the local kernel is more accurate. The second shows that raw data is indeed more beneficial to image super-resolution task. The third one is the change in the way the equation is solved. Obviously the joint estimation has the best performance. Another experiment is about the number of bases of the subspace. By combining different permutations of dk and dx, we can see that the optimal choice are dk equal to 4 and dx equal to 8. To summarize, we propose the first SSR method in the raw-to-raw domain for real data. The subspace constrained minimization reformulates the highly ill-posed SSR problem into a well-posed one. Experiments have shown that our method outperforms previous approaches both in metrics and in visual quality. Thanks for watching.